Thank you for coming to this presentation about our work at QC Ware that we did with Boehringer Ingelheim. Yes. So we looked at what we could do to push the performance of quantum phase estimation for chemistry. So the first question is, why do we think we want to use quantum computers for chemistry? So we hear that quantum computers can give an exponential advantage for chemistry. What exactly does this mean? On classical computers today, we have methods that can simulate chemistry. So this full CI method, for example, will yield exact results for all molecules. But the problem is that it scales exponentially. We have other methods that are more approximate. So this is an example. It's a coupled cluster method. It scales polynomially as n to the 7th, so that's pretty steep, but it yields really good results for well-behaved molecules. But for other molecules, like strongly correlated systems, which include transition metals or materials with like really interesting properties, it becomes inaccurate. And then something that probably you heard about, DFT. This scales as n cube, so that's density functional theory, and it's often accurate for well-behaved molecules, but it doesn't work either for strongly correlated molecules. And so this method is widely employed in the industry for simulations. Now, on the quantum computer, we can use quantum phase estimation. There are also other algorithms. We just heard about VQE. But quantum phase estimation can give you exact results with a scaling, depending on the implementation, that's around n to the 5. So that means if DFT is too slow for your problem, quantum phase estimation is not going to help you here. But if you need more accuracy for your problem, then you can use quantum phase estimation and potentially obtain exact results for your system. One important thing to note is that favorable scaling is different from having a practical runtime for systems of interest. So with our partner at Boehringer Ingelheim, we think it's very important to have a concrete problem for which we estimate the runtime of the algorithm, so we can really understand where we are at with respect to practically running these algorithms. So for that, I'm going to talk a little bit about what we need to understand to know the cost of quantum phase estimation. So the goal is to get the ground state energy of the Hamiltonian being a description of the molecule, with a given precision epsilon. And for that, we need one thing. We need to be able to encode the Hamiltonian into a unitary matrix U, because unitary matrix is what can be translated as a quantum circuit on the quantum computer. So the 4 main components of the QPE algorithm are the initial state preparation. So we have to have some kind of initial starting point for the algorithm, and it needs to have an overlap with the ground state, the true ground state of the molecule. And the probability of success of the algorithm actually depends on that overlap. Then what we do is we take that matrix U and we apply it several times. And the number of times we have to apply it depends on the inverse of the precision we need. And then we have a translation of the result into the computational basis and the measurement. These 2 last steps are not very important for the cost of the algorithm. So currently, the best way to encode molecular Hamiltonian is this qubitization way. And we're not going to dig into the details, but basically, we represent the Hamiltonian as we encode the arc cosine of the Hamiltonian in this matrix. And what we need, and what is important for the cost of the algorithm, is we need to normalize the Hamiltonian. So lambda here is the norm of the Hamiltonian, and we want to make sure that all the energies of the Hamiltonian are basically between -1 and 1. So we divide by that constant. And that also means that the precision we need for evolving U is epsilon divided by lambda, so we can get the precision epsilon on the final energy of the Hamiltonian itself. So we have a factor lambda over epsilon that goes into the cost of QPE. So the total cost is described as this expression. We have lambda over epsilon that gives us the precision at which we want to run the algorithm. And then we have this factor that depends on the initial overlap. And finally, also the cost of U itself counts in the cost. So if we take an example, and this is the central cluster of the FEMOCO protein that is able to take nitrogen from the atmosphere and make it into something useful. So that's a very interesting reaction for the industry. And if we want to describe this system right now, it's beyond the possibilities of classical computers. And so the latest estimates for the best implementation before our work were that you need about 2,100 logical qubits and 5 billion gates to be able to get the ground state energy of that system. In addition, there's a recent paper that estimated the initial overlap of a standard initial starting point for QPE, and it was 10 to the minus 7, which was like a very low success probability of the algorithm. So we want to try to address this issue, making a better starting point so we have a higher success probability of the algorithm. And we also wanted to see if we could reduce the resource requirements so that we can run this problem earlier on quantum computers. So this is, again, the expression for the cost, and we attacked it with two different ways. One was increase P0, and the other is decrease lambda. So I'm going to start by talking about how we went about increasing this success probability. So the most common way to prepare an initial point for QPE is simply to create one Slater determinant. So that's just a configuration of the electrons inside the orbitals of the molecule. Each orbital is 1 qubit, and then we just assign electrons to a given qubit. So it's very simple. It's a single layer of gate. There's other methods that create better initial states, but then you have to pay for that in terms of the number of gates in your quantum circuit. So our idea was, is it possible to pay more classical resources and keep the quantum circuit very simple and still obtain an improved starting point? And there was a recent paper by Norm Tubman and collaborators that showed that if you have classical methods, you can actually approximate the overlap with the ground state much better than the energy. So here we have a result where as you move to the right, you have a more and more approximate classical, a more and more accurate classical approximation. And we see that the overlap with respect to the true ground state is already pretty much converged at the first point, whereas the energy in blue is very hard to get right. And so the idea is that maybe we can use a classical approximation of the ground state to obtain a good approximation to the overlap. And from this approximation, we can optimize the representation of the Hamiltonian to increase the overlap of the initial starting point of QPE. So I see that, unfortunately, the plots are here, but they're missing all of the data, which is very sad. So I'm going to explain what should be on the plots. Here we compare our method, which is using optimized orbitals, to other methods that use the simple naive state preparation, and the other one that uses like a deeper quantum circuit. And what we saw is that in all cases, we are able to optimize the overlap by about 1 to 2 orders of magnitude, especially when compared to the naive method. We get up to 2 orders of magnitude there. But even compared to the CSF method, where you use a deeper quantum circuit, we were able to obtain a better overlap with a very simple method that just uses one single layer of gates and some classical resources. We also looked at the performance for cytochrome P450 that was already mentioned earlier today. It's a very important a molecule for the metabolization of drugs in human beings, important for pharmaceutical applications. In that case, the initial overlap is already pretty high, so we don't have to worry about it too much, and our method still yields a small improvement. You couldn't see it here, but the overlaps for the systems we looked at that are small models of this FEMOCO cluster, they are around 10 to the minus 3, and so they're already pretty low. So that shows that our method tends to improve the overlap better when the overlap is already low, which is good. Okay, so the next way we looked at the problem was to decrease this lambda, which is the norm of this Hamiltonian. So recently there was a paper that showed that lambda has a lower bound. So it's bounded by the spectral range of the Hamiltonian. So difference between the highest and the lowest energy of the Hamiltonian. That means this lambda, it generally depends on how you choose to represent your Hamiltonian. So that's how you can improve lambda or have it being worse than the lower case. But whatever you do, if you still have the same Hamiltonian, it can never be lower than this spectral range. However, this limit doesn't take into account any of the symmetries we find in the Hamiltonian. So this can be special symmetries if the molecule has some symmetries that exist, or it can also be the number of particles you have in the Hamiltonian. In chemistry, the number of particles is generally fixed, and so you just want to look at the number of particle sector of the Hamiltonian. That's important for your application. And so we derived a hierarchy of bounds looking at these symmetry sectors of the Hamiltonian, where the first bound is the one that was originally derived. That's the full energy range of the Hamiltonian. In the second bound, we consider that we can shift around symmetry blocks of the Hamiltonian that we are not interested in because we don't care about changing their energy. And in that case, the bound becomes the largest energy range of a symmetry sector. And the best bound is the one that only looks at the symmetry sector that we are interested in, and that's the spectral range of that symmetry sector. So that gives us a hierarchy of bounds that increasingly make use of symmetry, and that are also increasingly difficult to apply in practice because getting only the symmetry sector you want requires a lot of transformations of the Hamiltonian. So we estimated what the values of these bounds were using approximate classical methods, and then we looked at what the current performance of tensor factorization methods is compared to these bounds. So currently for these three systems, we have about a factor of 2 difference between what the tensor factorization methods can do and what the bound is without taking symmetry into account. So that's the first line here. However, if we take symmetry into account, then we can get up to an improvement of 20 on that. And so we can further reduce the resources required by the quantum algorithm. However, for that, we need to have a symmetry-aware tensor factorization of the Hamiltonian. And so that's what we designed. We took 2 methods that already existed, double factorization, and this other method that's symmetry shifting. So in this method, people are doing what I was talking about earlier. They are modifying the Hamiltonian in symmetry sectors that we don't care about. For example, if you know that your molecule has 10 electrons, the parts of the Hamiltonian that describe what happened when you have 8 electrons or 20 electrons, you don't care about them. So you can shift them around to modify the norm of your Hamiltonian. Now we combine both of these techniques into a single cost function that gives us this symmetry compressed double factorization of the Hamiltonian. So it's an approximate representation of the Hamiltonian, but the error we are making is very well controlled. And we can optimize this cost function to get the Hamiltonian representation we need. So when we look at the case of FEMOCO, we have a table here with resource estimates for existing algorithms. So the previous best was THC with 5 billion gates, 2100 qubits. And when we use our method, we can get down to 2.5 billion gates. So we have a factor of 2 improvement here at the cost of a larger number of qubits. But actually, we can change a little bit the details of the implementation of the algorithm. And if we pay a small price in terms of the number of gates, we can reduce the number of qubits too. And so then we get to an implementation that's effectively a factor of 2 better than the previous one without having to pay for it in terms of the number of logical qubits. Okay, so to conclude, the cost of QPE depends on 3 main factors. The norm of the Hamiltonian that we can modify by using Hamiltonian representations that are different. This initial state overlap, and then the cost of implementing this U representation of the Hamiltonian. With our method for initial state preparation, We use optimized orbitals that are obtained on a classical computer to improve the overlap by 1 to 2 orders of magnitude without using quantum resources. We derived some bounds on this norm that reveal the maximum possible improvement we can hope for using tensor compression techniques. And then we derived a new tensor compression technique that improves the gate requirements of QPE by a factor of about 2. With that, I would like to acknowledge my collaborators at QC Ware and at Boehringer Ingelheim that participated in that work, and I'll be happy to take any questions if we have time. Thank you.